The topic we'll be discussing in this lecture is GPRS, General Packet Radio Service. So basically GPRS provides packet mode transfer for applications that exhibits traffic patterns such as frequent transmission of small volumes of data or infrequent transmission of small or medium volumes of data. So basically GPRS is used either to transmit frequent transmission of small volumes of data or for infrequent transmission of small or medium volumes of data. So, so these are the two primary purpose it is used. GPRS should use the existing network resources more efficiently for packet mode application. So basically there are two modes in which data are transmitted over internet. That is either it is circuit switched or packet switched. So GPRS follows packet switched approach. So that the name is General Packet Radio Service. So it should use the existing network resources more efficiently for packet mode application. And it should provide a selection of QoS parameters, quality of service parameters. And also it should provide services like broadcast, multicast and unicast services. Broadcast means sending information to everybody. Multicast is sending information to selected groups. Unicast is sending information to one person. So the overall goal of GPRS is in this context is to provide a more efficient and cheaper packet transfer service, typically for internet applications. So network providers typically support this model by charging on volume and not on connection time. Basically, uh, it is supported based on the volume, not on connection time. So the main benefit for the GPRS user is it is always on characteristics. There is no need for connection setup. Connection setup is not required. It is something which is always on. GPRS was basically driven by the tremendous success of packet oriented internet and also by the new traffic models and applications. But GPRS needs some additional network elements. That is, it needs some additional softwares and hardwares. So GPRS needs some additional network elements like additional software. So as we have already discussed, one of the main characteristics of GPRS, it is always on. There is no connection setup is required because GPRS is mainly used to provide data service. It is not used for voice service. It is for data service. That is accessing internet, accessing your email. Such services are offered by GPRS. Okay. So the main concept of GPRS is for new GPRS radio channels, the GSM system can allocate between 1 and 8 time slots within the TDMA frame. So for new connections, it may allocate somewhere between 1 to 8 time slots within the TDMA frame. Time slots are not allocated in fixed pattern. It is not allocated in fixed predetermined pattern, but the time slots are allocated based on demand. Based on demand, these time slots are allocated. Okay. And all these time slots can be shared by the active users. And for every user, there will be an uplink and also downlink. Uplink and downlink will be allocated separately for each users. And allocation of these slots is based on current load and operator preferences. If some operators prefer certain slots more, and also based on the load, based on these two factors, the allocation will be done. For GPRS, operators often reserve at least a time slot per cell to guarantee a minimum data rate. These operators will reserve at least one time slot so that they can guarantee the minimum data rate. The GPRS concept is independent of channel characteristics and channel type and does not limit the maximum data rate. So, so, so the channel characteristics or channel type, all these cannot influence the data rate that is offered by the GPRS. And, and GPRS service can also be used along with the conventional services. GPRS service can also be used along with the conventional services. Now let us see the typical data rates uh, that are that are available with the GPRS. So there are different coding schemes available like CS1, CS2, CS3, and CS4. So different coding schemes are used depending on the error rate of the channel, depending on the error rate, and also depending on the error correction capabilities of the uh, coding scheme. Okay, so depending on, see, some of these coding schemes will provide better error correction capabilities. Some of these coding schemes will not provide better error correction capabilities. So depending on the requirement, the appropriate coding scheme will be used. For example, if a particular if a particular application can tolerate error, then CS4 will be used because it does not provide any error correction capabilities. Okay, CS4 coding scheme 4, it will not provide any error correction facility. So if a user is using an application which can tolerate more errors, then this scheme can be used. If somebody is using an application which cannot tolerate even a small error, then CS1 should be used. Okay, like that. So these are the various coding schemes and the data rate available with different slots. So with CS1, if there is only one slot, then the data rate available is 9.05 kilobits per second. So everything is in kilobits per second here. If there are two slots, then it's just double of this, almost double. So it will be 18.1 kilobits per second. If it is three slots, then it will be 27.15 kilobits per second. Like that. If it is eight slots, then it will be 72.4 kilobits per second. Okay, 9.05 into 8. That's it. Similarly, if CS2 is used, then in first, if it is there is only one slot, 13.4 kilobits, two slot, 26.8 kilobits, so on and so forth. CS3, so like that, these are the different data rates offered by the GSM under different coding schemes. And these coding schemes vary with respect to the error correction capabilities they offer. Uh, so the CSM system will choose an appropriate coding scheme depending on the error rate. Okay. So, and another important thing is the real available data rate heavily depends on the current load of the cell. As GPRS uses only idle time slots. GPRS uses only idle time slots, so it depends on the current load also of the cell. That is, there is no separate allocation of slots for GPRS, so it uses only the current idle slots. So the load on the system may also influence the data rate. Right? Data rate depends on the data rate also depends on the capability of mobile station because not all devices are able to send and receive at the same time. Okay, so different mobile stations may have different types of capacity, right? So, so here is an example. which shows example for device classes together with their ability to use time slots for sending and receiving data. So here is a class 1 device which can receive in one slot and it can send in one slot, and maximum it can use only two slots. This is a class 2 device which can receive in two slots and send in one slot, and maximum slots it can use is 3. Here is device 3 which can receive in two slots and send in two slots, but the maximum slots it can use is only 3. See, even though it can receive in two slots and send in two slots, it cannot use all the slots because its maximum limit is only 3 slots. So if it is receiving in two slots, then it should send in one slot. Or if it is sending in two slots, it should receive in one slot. Somewhere it should compromise because it is controlled by the maximum number of slots. Similarly, if you see this, here the device of class 5, it receives in two slots, it can receive in two slots and it can send in two slots, and the maximum slot is 4. The device which is on class 8, it can receive in 4 slots and send in one slot, and the maximum available slot is 5. The device in class 10, it can receive in 4 slots and send in 2 slots, but the maximum slot available is only 5. So it can, if it is receiving in 4 slots, then it can send only in one slot. If it is sending in all the 2 slots, then it can receive only in 3 slots. Similarly, class 12, it can receive, the device in class 12 can receive in 4 slots and can send in 4 slots. But its maximum number of slots that it can use is 5 slots only. So if it is receiving in 4 slots, then it can send only in one slot. Or if it is sending in four slots, then it can receive in only one slot. Or it can receive in 3 slots and send in 2 slots. Some combination of slots, but it should not exceed 5. So that's the point. Okay. So the maximum number of slots uh, should be uh, that is the key. Okay. So depending on the maximum number of slots, accordingly only the devices can use. Okay. So using all 8 slots, if some device is using all 8 slots for data encoding, using CS4 yields the maximum data rate of 17.12 kilobits per second. So the previous diagram we have used, see. So you can see here the data rate of CS4 is greater than CS3, and CS3 is greater than CS2, and CS2 is greater than CS1. So data rate is basically increasing in this way from top to bottom. Okay. So CS4 is offering the highest data rate. So CS4, if 8 slots are there, then it will provide a data rate of 171.2 kilobits per second. If some application is using this CS4 with 8 slots, then it will get a data rate of 171.2 kilobits per second. Okay. Typically, today's mobile station is a class 10 device. It's a class 10 device and it uses CS2. The normal mobile phones that we use, it uses the coding scheme CS2, and it provides a data rate of 53.6 kilobits per second for receiving. That is, for receiving, it uses 4 slots. Okay, so 53.6 kilobits per second. And for sending, it provides a data rate of 26.8 kilobits per second. That is, it uses uh, 2 slots. Okay, so totally it uses 6 slots, 4 slots for receiving and 2 slots for sending, and it's a CS2. So for receiving, the data rate is 53.6 kilobits per second, and for sending it is 26.8 kilobits per second. Okay, so let us continue. So yeah, so So in phase one, GPRS offers a point-to-point packet transfer service. So point-to-point is called as, in short, PTP. What it is called as PTP. So one of the PTP versions offered in the PTP connection oriented network service. So, which is called as PTP cons. One of the PTP versions offered is one of the PTP version is called as, basically, GPRS offers a point-to-point packet transfer service, and one of the point-to-point service is called as PTP connection oriented network service. So which is called as PTP cons. So this includes the ability of GPRS to maintain a virtual circuit. This includes the ability of a GPRS to maintain a virtual circuit upon change of the cell within the GSM network. Okay. So it maintains something like a virtual connection with the user. This type of service corresponds to X.25. Okay. The other PTP version offered is PTP connectionless network service. So basically, the point-to-point service, there are two types of service. One is connection-oriented service. The other one is PTP connectionless service. So PTP connection-oriented service is called as PTP CONS, and the PTP connectionless service is called as PTP CLNS. So this supports applications that are based on Internet protocol. Okay, multicasting, called point-to-multipoint service. Uh, all these are left for GPRS phase 2. So, and the users of GPRS can specify a QoS profile, quality of service. That is, what are the minimum quality of service that they are expecting, that the users can specify. And this will determine the service precedence. This will determine the uh, service precedence. Okay, like whether the service should be high, normal, or low, or reliability class or delay class. So QoS profile, that is, the user can specify a QoS profile. Based on that QoS profile, the GPRS service will be offered to the user. Okay. So there are three types of service: high, normal, and low. Okay. And this is also characterized by reliability class and delay class of the transmission, and also through user data throughput. GPRS should also adaptively allocate radio resources to fulfill these user specifications. The radio resources should be allocated to fulfill these user requirements. So, this particular table, it shows the um, various probabilities of a service data unit. Various probabilities of service data units. Uh, if the service data unit is 128 byte, then what type of service will be assured? And if the service data unit is 1024 bytes, then what type of service will be assured? Okay. So there are three reliability classes together with the maximum probabilities of lost service data unit. Okay, so there are three types of things can happen. One is lost service data unit, or the so the three things can happen. One is lost service data unit, the other one is duplicated service data unit, and the other one is uh, service data unit out of original sequence. Okay. So lost service data unit means some packet is getting lost. So that comes under lost service data unit. Duplicated service data unit means some packet is duplicated. Okay, and SDU out of original sequence means some packet is coming not in the particular sequence. The sequence is getting changed. Okay, so this this is what is represented in this table. And reliability class 1 could be used for uh, very error sensitive applications that cannot perform error corrections themselves. So, so these are the various uh, reliability classes. These are the various reliability classes. Yes, let us refer this particular table. So, so these are the various reliability classes. These are the various reliability classes. Class 1, 2, 3. Okay. So reliability class 1 will be used. Reliability class 1 will be used for error sensitive applications that cannot perform error corrections themselves. In that case, reliability class 1 will be used. Okay. So for reliability class 1, the probability of SDU getting lost is 10 to the power minus 9. And the probability of duplicate SDU is also 10 to the power minus 9. Out of sequence is also 10 to the power minus 9. Corrupt packet is also 10 to the power minus 9. That is, whether getting lost or duplicate or out of sequence or corrupt, all these are very, very low. Okay, because the application itself cannot correct errors. So in that case, reliability class 1 will be used. Okay. And if applications exhibit greater error tolerance, then class 2 would be appropriate. If the applications can do lot of error tolerance by themselves, then class 2 can be used, which has a loss probability of 10 to the power minus 4, duplicate probability of 10 to the power minus 5, out of sequence probability of 10 to the power minus 5, and corrupt SDU probability of 10 to the power minus 6. And class 3 is for error insensitive applications that can handle error themselves. So class 3 is used when an application can completely handle error by itself. Okay. So here loss probability is 10 to the power minus 2, duplicate probability is 10 to the power minus 5, out of sequence probability is 10 to the power minus 5, and corrupt probability is 10 to the power minus 2. So if the applications cannot handle the error by themselves, uh, then class 1 will be used. If the application can exhibit a good error tolerance, then class 2 will be used. If the applications can handle totally all the error by themselves, then class 3 will be used. Okay. So, so this is how the various service data units and the dependent and the different reliability classes were used in GPRS. Okay. Now let us discuss about uh, delay. Okay. So we have discussed so far about reliability. Now we are moving to the another characteristics, which is delay. So delay within a GPRS is incurred by the channel access delay, coding for error correction, and transfer delays in fixed and wireless part of the GPRS network. So these are the reasons why delay can happen. Delay can happen because of channel access delay. The station is unable to access the channel due to some reason, or there are some task related to error correction is going on, or there is some transfer delay, data transfer delay in fixed or wireless network. Because of these reasons, there may be delay. Okay. The delay which is introduced by the external network is out of scope. That cannot be dealt by GPRS. If any delay is introduced by some other sources, some fixed network, okay, there, and because of that, the user inside the GPRS is experiencing delay, so that is out of scope because GPRS can't do anything about that. Okay. But GPRS does not produce any additional delay by buffering packets. Okay, so GPRS don't do any buffering kind of thing, and because in order to make sure that there is no delay because of that. Okay, and GPRS always forwards packets as fast as possible. Right. So this particular table, it shows the specified maximum mean and 95% delay values for packet size of 128 and 1024 bytes. Okay. So for packet size of 128 byte, the mean delay for class 1 is, for delay class 1 is less than 0.5 second. For class 2 is less than 5 seconds, and for class 3 is less than 50 second. So class 1 will be used for delay sensitive applications, highly delay sensitive application. Highly delay sensitive application means what? Some say, say you are making some financial transaction that can be treated as a highly delay sensitive application. You cannot tolerate any delay. Okay. And class 2 will be used for applications that can tolerate delay up to certain extent. So here the mean delay is less than 5 seconds. And class 3 will be used for delay insensitive applications. Okay. So here the delay can be up to less than 50 seconds. Okay. Say for example, you are watching a cricket match, that will come under class 3, because if you are watching cricket's a match less than 50 seconds, that is not going to affect anybody, right? With 50 seconds delay, if you are watching, I think that's not an issue. Okay. Similarly, this is the 95 percentage delay, 95 percentile delay. So this is the delay part for 128 uh, size of 128 byte packet, and this is the delay for 1024 byte packet. So this is how the delay characteristics of GPRS was specified. Okay. So so you can see all delays or orders of magnitude higher than fixed network delays. Okay. So basically the delay produced by GPRS is higher than the fixed network. Okay. So this is very important characteristics. This important characteristic has to be taken into account when implementing the higher layer protocols like TCP on top of GPRS. Okay. And typically the round trip time in fixed networks are in order of 10 to 100 milliseconds. Okay. Using GPRS networks, round trip times will be above 1 second. So in fixed network, the round trip delay is only between 10 to 100 milliseconds. But with GPRS, the round trip delay will be more than 1 second, even for small packets. Even for small packets whose size is somewhere between 128 to 512 byte. Even for such packets, the delay will be more than 1 second. Okay. And GPRS also exhibit jitter compared to fixed networks. Jitter in the sense it may create lot of what you call instability in the signal. Instability in the signal. So this characteristics also has a strong impact on user experience. Okay, especially when the user is working on some interactive internet applications. So this jitter will provide a bad experience for the user. GPRS also includes several security services, which we have already discussed, such as authentication, access control, user identity, confidentiality, and also anonymous service is also possible. Anonymous service is also possible. Example applied for a road toll. So if you are using GPRS for road toll, only the amount will be charged, but who is the user identity will not be revealed. Okay. So these are the so this is the general information about GPRS. So next we shall discuss the GPRS architecture. Next we shall discuss the GPRS architecture. So GPRS architecture introduces two new elements and compared to the mm, GSM architecture. So these are GPRS support nodes, which is called as GSM. So basically, this is a router. This GSM is GPRS support node. Basically, this is a router. All GSMs are integrated into standard GSM architecture. So these GSMs are already integrated into the standard GSM architecture, Global System for Mobile Communications architecture. And there is a gateway GPRS support node. There are two new elements. One is GPRS support node and the other one is a gateway GPRS support node, GGSN, which is the one uh, which which interconnects GPRS network with the external packet data networks, EDN. So the GSN, gateway GPRS support node is the one which interconnect GPRS network with the external packet data network. Okay. So this node contains routing informations for GPRS users. It performs address conversions and tunnels data to a user via encapsulation. Okay. So this gateway GPRS, it does all these things. It, it contains routing information for GPRS users. It performs address conversion and it tunnels data to a user via encapsulation. Okay. And the GGSN is connected to external networks via GI interface. It is connected to the external network via GI interface. So this diagram represents the uh, G, GPRS architecture. Okay. So here we can see there is something called as uh, G, GSM. Okay. So so here we have GGSM. So as we have already discussed, GGSM is nothing but gateway GPRS support nodes. Okay, and there will be GSN also. Okay, in this diagram it is not shown. So GSN will be connected with the GGSN, and this GGSN will be connected to what you call, it will be connected to the fixed networks like PDN, public data networks, IP, X.25 and other networks. And whenever it is connected with the fixed network, it is connected through an interface, and that interface is called as GA interface. It is connected with the fixed network through an interface, and that interface is called as GA interface. So this is the GA interface. So the packet data is transmitted from a PDN. The packet data is transmitted from a PDN, public data network, through the GGSM and through the GGSM and SGSM. Okay, there is another element called SGSM. So there is another element which is called as SGSM. So SGSM stands for servicing GSM, servicing GPRS support node, which supports MS via the GB interface. So here we can see there is SGSM. This is servicing GPRS support node. Okay, so it is connected with the BSS via the GB interface. It is connected with the BSS via the GB interface, and through BSS it will be connected through MS. Okay, so basically it is connected with the MS via through BSS via the GB interface. The SGSM, it will request user address from GPRS register. The SGSM will request user address from GPRS register. So GPRS register is called as GR, and it keeps track of the individual mobile station's location. It is also responsible for collecting billing information and performs several security functions such as access control. Okay. The SGSN is connected to a BSC via frame relay. It is also connected to BSC via frame relay and is basically on the same hierarchy level as an MSC. SGSN is in the same hierarchy level as the MSC. So the GPRS register, already we have discussed GR. The GR, that is the GPRS register, is normally a part of HLR. It is normally a part of HLR, and it stores all GPRS relevant data. It stores all GPRS relevant data. All data relevant to the GPRS will be stored in GR. Okay. So GGSN and SGSNs can be compared with home and foreign agents. Okay. So GGSN, you can say it is a GGSN can be treated as a home agent, and SGSN can be treated as a foreign agent. So, so the packet data is transmitted from a PDN, public data network, via the GGSN, and then it passes through SGSN, and then it will go to the BSS, and finally to the particular mobile station. So this is the path. So if the data is coming from the fixed network, so it will first go through the GGSN, and then to SGSN, and then to BSS, and finally it will reach the MS. Okay. So this is the particular path it takes. Okay. So so the MSC is responsible for data transport in traditional circuit switched GSM. Here it is used only for signaling in the GPRS scenario. In the normal circuit switched scenario, MSC is responsible for data transport. But in GPRS, it is used for only signaling purpose. Okay. So before sending any data over the GPRS, an MS should first attach to it, following the procedures of mobility management. Following the procedures of mobility management, the MS should first uh, attach to it. Okay. So the attachment process includes assigning a temporary identifier called temporary logical link identity. So the attachment process includes assigning a temporary identity called temporary logical link identity for the mobile station. And also it includes a ciphering key called ciphering key sequence number. For so basically that key is used for data encryption. So for each mobile station, a GPRS context is set up and stored in the mobile station. So for each mobile station, there will be something called as a GPRS context, and this GPRS context will be stored in the mobile station corresponding to the SGSN servicing GPRS support node. Okay. So this context it includes the status of the MS, like whether the MS is ready or idle or standby. Okay. All these informations will be available in this GPRS context. Okay, for each MS there will be a GPRS context. The GPRS context will include information like whether the MS is ready, idle, or standby. The CKSN, which is basically a flag. The CKSN, which is basically uh, a flag. So it is also a cipher key sequence number. Cipher key sequence number. It's a flag indicating if compression is used or or routing data. These informations will be available in so along with the CKSN, along with the cyber along with the cipher key, there is a flag. There is a flag also will be stored in the GPRS context, and this flag includes informations like whether compression is used or or routing data. All this information will be stored here. Okay. Besides attaching and detaching mobility management, also comprises functions for authentication, location management, and ciphering. Other than attaching and detaching the mobility management, so the attachment and detachment of mobile station is done by mobility management. Other than that, it also includes functions for authentication, location management, and ciphering. Okay. In idle mode, an MS is not readable. If the MS is not idle, it is not reachable. And in the idle mode, if the MS is idle, then it is not reachable, and all context is deleted, and all context about the particular MS will be deleted. In the standby state, only movement across routing areas is updated to SGSN, but not changes of the cell. If it is in the standby mode, if the mobile station is in the idle mode, then it is not reachable, and all the context information in the mobile station will be deleted. If it is in the standby mode, only movement across routing areas is updated to the SGSN, but not changes of the cell. It is if the mobile station is moved from one cell to another cell, that information will not be updated. Okay. Permanent updating would waste battery power. So no updating would require system-wide paging. So the update procedure in standby mode is a compromise. Only in the ready state, every movement of the MS is indicated to the SGSM. So there are three states. It can be idle, standby, or ready. If the mobile station is in the ready state, then every movement of the mobile station will be updated to SGSM. If it is in standby mode, then where the routing information alone will be updated. But if the mobile station moves from one cell to another cell, that won't be updated. If it is in the idle mode, then the mobile station will not be reachable. Then the mobile station will not be reachable, and all context will be deleted. All context will be deleted. Okay. So so this is about the architecture of the GPRS. I mean architecture, reference architecture. So next we will discuss the packet architecture of GPRS. Next we shall discuss the packet architecture of uh, GPRS. Okay. So all data within the GPRS backbone, that is between GSMs, is transferred using GPRS tunneling protocol. There is a protocol called GPRS tunneling protocol, and 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 all data transfer and all data within GPRS backbone, that is between GSMs, is transferred using the GTP, that is GPRS tunneling protocol. And this GTP can use two different transport protocols. This GTP transfer GTP stands for GPRS tunneling protocol, and this GTP can use two different transport protocols. Either it can use the reliable TCP, or it can use the unreliable UDP. Okay, so TCP is used for X.25 packets, and UDP is used for IP packets. TCP is used for X.25 packets, and UDP is used for IP packets. Okay, so the network protocol for the GPRS backbone is IP. The network protocol for the GPRS backbone is IP. Okay, so to adapt to the different characteristics of the underlying network, the subnetwork uh, dependent convergence protocol is used between an SGSN and MS. So there may be different types of networks. Okay, so in order for the GPRS to adapt to all these different types of networks, the subnetwork dependent converging protocol, there is a convergence protocol called subnetwork dependence convergence protocol, and this convergence protocol will be used between SGSN and the MS. Okay, MS is mobile station, and SGSN is the gateway GPRS support node. Okay. So on the top of SNDCP and GTP, user user packet data is tunneled from the MS to the GGSM. On top of SNDCP, SNDCP is Subnetwork Dependent Convergence Protocol. On top of SNDCP and GTP, user data packet is tunneled from MS to the GGSM, and vice versa. That is uh, that is that is along with the user packet will be what you call the user data packet will on the top of the user data packet will be sent on the top of SDNCP. SNDCP. SNDCP is used in order to adopt GPRS with the different types of networks. Okay. So the user data will not be transmitted just like that. It will be transmitted on top of SNDCP and GTP. Okay. So to achieve high reliability of data transfer between SGSN and MS, a special LLC is used, logical link control is used, which includes uh, which includes uh, to achieve high reliability of data transfer between SGS and MS. A special LLC is used, which comprises ARQ and FEC mechanism. Okay. FEC is forward error correction. ARC is automatic request. Okay, automatic resource request. That is if any packet is missed, then it will automatically request that particular packet, give back that packet like that. So these are introduced to achieve high reliability of data transfer between SGSN and MS, that is the mobile station. Okay. So the base station subsystem, the base the base station subsystem GPRS protocol, which is called as BSSGP, is used to convey routing and QoS related information between BSS and SGSN. Okay, so there is a protocol called uh, BSSGP, which stands for Base Station Subsystem GPRS Protocol, and this protocol is used to convey routing and QoS related information between BSS and SGSN. Okay. So this particular protocol BSSGP, it does not perform error correction, and it works on top of frame relay. It does not perform error correction, and it works on top of frame relay network, which is called as F4. Frame relay networks is also called as F4. And the radio link control, RLC, the radio link control, RLC, okay, provides a reliable link, while the MAC control access with signaling procedures for radio channel. Okay. So RLC provides a reliable link, and the MAC control MAC control access the signaling procedures for radio channel and mapping of LLC frames on the GSM physical channel. Okay. The radio interface at UM needed for GPRS does not require fundamental change compared to standard GSM. The radio interface of GPRS does not need any fundamental change when compared with the standard GSM. Okay, so basically it is same as that of the standard GSM. Okay, that's the point. The radio interface at UM needed for GPRS does not require a fundamental change compared to standard GSM. Okay. However, there are many new logical channels and their mapping onto physical resources have been defined. Okay. There are many logical channels and their mapping to physical resources have been defined. For example, one MS can allocate up to 8 packet data traffic channels. One MS can allocate up to 8 packet data traffic channels, PDTCCHs. PDTCHs. Okay. Capacity can be allocated on demand or shared between circuit switched channels and GPRs. The capacity can be allocated on demand or it can be shared between circuit switched and GPRs. So this allocation can be done dynamically with load supervision, or alternatively capacity can be pre-allocated. So the allocation can be either dynamically done with load supervision, or it can be pre-allocated. It depends. Okay. So basically this diagram shows the protocol architecture of GPRS. Okay. So in MS, these are the various layers: radio, MAC, RLC, radio link control, LLC, logic link control, uh, SN DCP, subnetwork dependent convergence protocol, IP or X.25, and other applications. Okay. And these are the layers in BSS. Okay. So in BSS we have BSS GP, which is base station subsystem GPRS protocol, and these are the layers in SGSM. Okay. So and these are the layers in GGSM. So yeah, a very important factor for any application working end to end is that it does not note any details from the GSM or GPRS related infrastructure. Okay. That is, the end user does not know whether he is availing service from GSM or from GPRS. The application uses example TCP on top of IP. IP packets are tunneled to GGSM, which forwards them into PDN, which forwards them into the PDN, public data network. All PDNs forward their packet to for a GPRS user to the GGSM. Okay, that is, if PDN is receiving any packet for a GPRS user, then it will forward to the GGSM. It will forward it to the gateway GSM. The gateway GSM asks the current SGSM for tunnel parameters. Then the gateway GSM will in turn communicate with the SGSM for the tunneling parameters and forward the packet via SGSM to the MS. And through the SGSM, the packet will be forwarded to the particular MS, that is the mobile station. So this is the communication path. Although, even though the MS using GPRS may be considered as part of the internet. So through GPRS, if you are accessing the internet from a mobile phone, although it is a part of the internet, we should know that operators typically perform address translation. Operators normally perform something called as address translation uh, in the GGSM using NAT. Using a concept called NAT, they perform address translation. NAT stands for network address translation. Okay. So all mobile stations are assigned private IP address, which are then converted into global addresses. This private IP address are converted to global IP address at GGSM. At GGSM. The advantage of this approach is the inherent protection of MS from the attacks. So, so that is, even though when the mobile station is connected with an internet, it has an IP address, but this IP address, his private IP address will be converted to some other IP address. And because of that, the device will be protected from the attack. That is nobody can identify that this IP address corresponds to this particular device. Like that, you cannot relate. So this is something like TMSI. In GSM, we have discussed in TMSI, that is in the air interface. The mobile phone's identity will not be relieved. Instead of IMSI, it will use TMSI. Similarly, here also the private IP address will be translated into a global IP address. Okay. So private IP addresses are not routed through the internet. So private IP addresses are not routed through the uh, internet. Okay. Uh, so it is not possible to reach an MS from the internet. So through internet, somebody cannot reach your mobile phone directly. So there is a disadvantage also in this case. If an MS wants to offer a service using a fixed globally visible IP address, that cannot be done. If a mobile station want to provide a service, if a mobile station want to provide a service, uh, for example, if you want to host anything using your mobile phone, that is not possible because your IP address is not your IP address is hidden. Okay, so this is a difficulty with IP4 and NAT. Okay, but in IPv6, but in IPv6, uh, it is something in a different way. Okay, but it will be interesting to see how IPv6 is used for all this purpose. But with IPv6, this is possible. Okay, so that's it about GPRS. So what we have discussed in the sense we have discussed in detail about the GPRS. So GPRS is basically it provides data service. It provides data service for the mobile users. GSM provides voice service. GSM basically provides voice service, and GPRS it basically provides the data service. What are the different types of services it provides, and what are the various uh, components in the GPRS architecture? All these things we have discussed. So mainly it provides packet oriented service, so that the name is general packet radio service. Okay, it provides broadcast, multicast, unicast service. It provides efficient and cheaper service, and we have discussed that the GPRS radio channel can range from 1 to 8 time slots. It provides both uplink and downlink, and different data rates for each coding schemes we have discussed. So there are different coding schemes from coding scheme 1 to coding scheme 4. Coding scheme 4 will be used when the channel is if the applications are not what you call are not error sensitive, and coding channel 1 will be used for if the applications are error sensitive. And then we have discussed for different class of devices how much receiving and sending slots can be. So the receiving and sending slots, basically it should be less than the maximum number of slots. So that is the main criteria. Based on that, the receiving and sending slots should be allocated. And then we have discussed uh, what is the loss probability of a SDU. Okay, that is data. What is the duplicate probability of a data unit? What is the out of sequence probability of a data unit? And what is the correct probability of a data unit? So, these probabilities are very low for reliability class 1. So again, it depends on applications. So if you are running a highly reliable application, then it should use reliability class 1. So if the application can tolerate some errors, then it can use reliability class 3. If the application uh, can tolerate mm, some amount of errors, not all errors, then it can use reliability class 2. Okay? So like that, there are different reliability classes, okay, which we have discussed, and then we have discussed like yeah. So what is the mean data rate for packet size of 128 byte and packet size of 1024 byte? So what we observed is Anyway, the data rate is very less when compared with the fixed networks. The fixed networks data rate is very high when compared with sorry the data rate is very the data rate is very high when compared with the fixed networks. The fixed networks the delays are very high when compared with the fixed networks, whereas in the fixed network the delay is very less. Okay, so the round trip time in fixed network is of the order of 10 to 100 milliseconds, whereas in GPRS the round trip time is above 1 second, even for a small packet of less than 512 byte. Then we have slightly discussed about the various security services offered by GPRS, and then we have jumped into GPRS architecture. We have understood what is SGSN. We have understood what is GGSN. So GGSN is a global GSM which connects with the PDN. It gets data from the PDN. It gives to SGSN, and through that the data will be communicated to the mobile station. So before sending any data, MS must attach by following the procedures of the mobility management. Then there will be a attachment process includes assigning a temporary identifier to the MS, which is called as temporary logical link identity, and there is a ciphering key sequence number CKSN. Okay. So and for each MS, the GPRS context is set up, and that GPRS context is stored in the MS itself, and that can hold three it can be at three states. It can be either idle or standby or ready. So if it is idle, then the mobile station cannot be reachable. If it is idle, the mobile station cannot be reachable, and uh, and all the context will be deleted. If it is standby, only movement across the routing area is updated, and changes from one cell to another cell will not be updated. Okay. So only if it is ready, then every movement of the mobile station will be updated to the respective SGSM. And then we have discussed the protocol architecture of GPRS. Okay, we have discussed what is RLC, radio link control, right? So that's it about the GPRS architecture. So let us stop here.